Assalamualaikum warahmatullahi wabarakatuh. Good morning, ladies and gentlemen. Welcome to all attendees for the event of the 5th International Seminar on Metallurgy and Materials. So, good morning, ladies and gentlemen. Assalamualaikum warahmatullahi wabarakatuh. Welcome again to the 5th International Seminar on Metallurgy and Materials, ISMM 2022, under the theme of Strengthening Research and Innovation in Metallurgy and Materials for Sustainable Economic Development. So our seminar has been held from yesterday, 22nd of November, and will finish this afternoon at 23rd of November, 2022. Let me introduce myself. My name is Taritas Maria from Research Center for Metallurgy as the Master of Ceremony today. Before it, I would like to greet the Head of Research Center for Metallurgy, National Research and Innovation Agency, PR Amprin, Ibu Dr. Ika Kartika, the Chief of International Seminar of Metallurgy and Materials, Dr. Agus Budi Prasetyo, our moderator for the second plenary session, Dr. Albertus Deni, and all guests of honors. Firstly, our first keynote speaker, Dr. Rizman Abdul Rahman Rashid from Swinburne University, Australia. For our second keynote speaker, Professor Dr. Muhammad Zaki Mubarak from Institute of Technology, Bandung, Indonesia. Our third keynote speaker, Associate Professor Dr. Lydia Helena Wong from Nanyang Technology University, Singapore. All academic communities, all today's presenters, all participants, and also all committees. So before we start the seminar, I would like to invite all guests for open your camera, and we're going to have an opening ceremony song for our national anthem, Indonesia Raya. So for everyone here, could you please open your camera? Okay, thank you. Then we will start for opening national song for Thank you. Thank you everyone for your participation. So before we start, I would like to invite all attendees here to open your camera since we will have a photo session. So for all participants, could you please turn on your camera? Okay, maybe we will have 3 times photo sessions, okay? 1, 2, 3. Okay, 2 more. 1, 2, 3. And the last one. 1, 2, 3. Thank you. We will have a plenary session pronto for metallurgy print. At our second plenary session, we have 3 keynote speakers. The first keynote speaker is Dr. Rizwan Abdul Rahman Rashid from Swinburne University, Australia. Our second keynote speaker, Professor Dr. Muhammad Zaki Mubarak from Institute of Technology Bandung, Indonesia. Our third, the discussion will be conducted directly once the keynote. The end of our plenary session around at 12:05, we will have a break and every presenters to prepare for the panel session. Then before it as well, I would like to ask name, for example, like BR1 if I am the Without further ado, I would like to invite our moderator, Bapak Dr. Albertus Denny.
Okay, thank you very much, Mbak Dalita. Okay, good morning, everyone. Okay, I'm sorry, is my voice clear? I hope it's okay. Okay, thank you very much. Okay, first of all, I would like to greet the head of research center for metallurgy, Dr. Ika Kartika, and the chairman of ISMM 2022, Dr. Agus Putri Prastyo, and also the plenary speakers today, Dr. Rizwan Abdul Rahman Rashid from Swinburne University, and then Professor Zaki Mubarak from ITB, and Professor Lydia Helena Wong from Nanyang Technological University. Okay, good morning, Bapak Ibu partisipan. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh.
Welcome to the second day of the International Seminar of Metallurgy and Materials. How are you? I hope everyone is doing well and still enthusiastic to listen and actively participate either in the plenary talks from now on and later in the parallel session. My name is Albertus Denny Setiawan from Research Center for Metallurgy BRIN, and it is an honor for me to chair the today plenary session. So then we will have 3 plenary talks here that as a scheduled. The first plenary talks will be about cold spray coatings and additive manufacturing delivered by Dr. Rizwan Rashid. The second talk will be about extraction of nickel, cobalt, and scandium by Professor Saki Mubarak, and then the third talk will be about advanced material for the next generation solar harvesting devices by Professor Lydia Wong. After each talk, there will be a Q&A or discussion session, and during the session, Bapak Ibu participant can directly click the raise hand button or write in the chat box if you want to send any question or comments. And please don't forget to say or write your name and institution before sending the question or comments. Okay, without too much delay, I will start the first plenary talk. Okay, Dr. Rizwan Rashid is available here, I think. Good morning or good day there, Dr. Rizwan Rashid.
Hello, assalamu alaikum wa rahmatullahi wa barakatuh.
Good morning. How are you today? I hope.
Alhamdulillah.
Thank you very much. Okay, by the plan, the first plenary talk actually will be delivered by Professor Suresh Paladisamy from Swinburne University of Technology, but it seems that Professor Paladisamy has another important agenda too today. So here we will have Dr. Rizwan Abdul Rahman Rashid to deliver the plenary talk. The title will be about application of cold spray coating and additive manufacturing. At first, I would like to introduce the biography of Dr. Rizwan Rashid. Dr. Rizwan Rashid has extensive research experience in materials and advanced manufacturing technologies and has worked in both academic and industrial environments. He has been working on powder-based manufacturing technology for more than 13 years and on various additive manufacturing process, including selective laser melting, SLM, laser additive deposition, LAD, and cold spray additive manufacturing. Dr. Rashid is currently working in cold spray additive manufacturing technology, which contrary to SLM and LED, which does not require a heat source to print metal parts. He was part of the team that examined the effect of copper coating on existing high-touch material surfaces on the inactivation of SARS-CoV-2 coronavirus and other bacteria such as E. coli and S. aureus. Further, the team has attended to work bulk copper, aluminum, and other light metal parts. Dr. Rashid was granted a PhD degree from the University of Queensland in 2013 and is currently a postdoc research fellow at Swinburne University of Technology. He has published more than 50 research articles in well-reputed T1, T2 tier journals, and this publication has been cited more than 1,450 times. Wow, it's incredible. And his current age index is 21. He has received many numbers of awards and also serving as a scientific peer reviewer for the selected journals such as in Elsevier and DPA. Okay, Dr. Rizwan Rashid, I think it's your time and your screen and time are yours now. Please.
Thank you very much, Dr. Albertus Denny. It was kind and humble words for me. Thank you to introduce me and provide my background. I'll just try and share my screen. Please let me know if it's visible to all. Are the slides visible?
Yes, it's
Thank you,
clear.
Ron.
But
So, before I begin with today's seminar and talk on applications of cold spray coatings and additive manufacturing, I would like to give a brief introduction to the team working behind this technology at Swinburne University of Technology. This team is led by Professor Suresh Palanisamy, who has been working at Swinburne University since 2013. And I have been working under him as a postdoc research fellow from that time since. Other colleague members of the team who have contributed massively to the projects in cold spray additive manufacturing is Dr. Nowana Otasoid, Dr. Krishnamurthy Prasad, and going to be Dr. Muhammad Abdul Khalid. I'm really honored and happy to present in the 5th International Seminar on Metallurgy and Material Science 2022. As evident from all the plenary talks that were given yesterday and the presentations happening, metallurgy and material science is a very interdisciplinary subject. It's involving all different topics and is not restricted to one particular area of research. So for today's talk, I will take into account additive manufacturing process, that is the cold spray additive manufacturing. And that can be applied to both coatings and 3D printing of self-standing parts. In today's talk, I will cover 4 basic topics. I'll introduce additive manufacturing and then a little bit fundamentals about cold spray process applicable to both coatings and coatings, repair, and additive manufacturing. And then give you 3 basic case studies on the effect of print part orientation during cold spray process, effect of post-build heat treatment, and effect of copper coating on aluminum and mild steel substrates that can fight against different microbes involving the COVID-19 virus. So what exactly is additive manufacturing? Before I delve more deep into the definition of additive manufacturing, let's talk about what conventional manufacturing involves. If we have a 3D object that needs to be fabricated, generally has complex features and requires multiple processes that needs to be carried out. In this case, subtractive manufacturing is more kind of used very often, where a material, where the process starts with the bulk material as a solid that's shown in A. Followed by using machining tools and other processes to remove the parts of the component that are not required, thereby generating a huge amount of waste. In the case of additive manufacturing, the cycle is reversed. We start with material that are in powder form or wire form, and we need to get to the 3D object. We need to get to the 3D object in here. And in the process, we generate very less waste because we are using more kind of raw materials that are suited to layer by layer printing. So additive manufacturing is nothing but printing for a designed part prototype where the raw materials are either in powder form or wire form and directly be converted into 3D object with less waste. So additive manufacturing offers a new class of manufacturing processes where parts are manufactured directly from a given computer model, like a CAD file, using layer by layer addition of material without using any tooling or fixtures that are generally required using conventional manufacturing processes. Now, these tooling and fixtures in the CNC machine would be more kind of cutting tools and the fixtures that go behind machining each and every feature on the component, whereas in formative processes where you're forming, casting, die casting, these tooling will involve die tools and molds that are required to solidify the melt material. Additive manufacturing is especially suited to those industries where the changes in product design are very frequent, where you have a prototype needs to be continuously modified, revised, and updated as the functionality of the part is to be improved or enhanced or changed. And the industries where you need to have really low lead times. So the product lead times generally are high in most other conventional fabrication industries. So additive manufacturing is an advanced manufacturing process that can be used in these industries. Sometimes you have parts that are limited to the design of the fabrication process, where you cannot implement complex features or complex shapes, which are not repeatable in other conventional fabrication techniques. Additive manufacturing, on the other hand, does not have this limitation. It can be used directly to produce parts that are complex in shape and geometries, whereas as well as customized designs for the parts that are used. For additive manufacturing, there are generally 5 processes that need to be taken place. We start with a CAD model, where the 3D model of the product is designed as per in the computer, converted into a stereolithography file, which is generally known as .stl file. This file is then sliced using a proprietary software of the 3D printers, whichever 3D printer you have in-house. And this sliced file is then fed input to the 3D printing system, where each of these sliced layers are printed consequently using any of the raw materials that are available in that machining, that 3D printing system. And the final stage is where the end part is finished, either by machining or by post-heat treatment. And eventually you'll have a final product which can directly be delivered to service. Metal additive manufacturing can be classified into various types. You have solid-based systems, we have powder-based systems, and then liquid-based systems. Within the powder-based systems, which is the topic of discussion for today, we have different types of techniques, more kind of involving laser-based systems, which is the selective laser sintering, also known as digital metal laser sintering, and selective laser melting. These two are powder bed additive manufacturing processes, where the powders are provided in the chamber and are consequently molten layer by layer. Other technique is the powder-fed laser technique, which is fused metal deposition or laser metal deposition, LMD in this case. And in all these 3 techniques, we have laser as the energy source used to fabricate the part. Other type of additive manufacturing technique is the electron beam melting, where the energy source is electron rather than the laser system. Electron beam melting is also a powder bed system, thereby requiring a lot of powders to start as to fabricate the component. A new addition to this family of metal additive manufacturing processes is the cold spray additive manufacturing. Let's dwell more in depth into what cold spray means and how it can be applied to additive manufacturing. So cold spray process is typically a process where powders, in this case metals, ceramics, and composite powders, are fed into a chamber. That chamber uses high temperature to heat the powders as well as the gas that is coming into the chamber, and subsequently delivered through a level nozzle, which is known as the level nozzle. And this compression results in high supersonic speeds of the powder that is ejected from the end of the nozzle and deposited onto a substrate. For the gas inlet, the type of gases that go into the chamber to heat the powders, it's typically nitrogen and helium. The system that we have at Swinburne uses compressed air because it's cheaply available and economical. Using these gases, the typical speed for the powders that is generated during the deposition process is about 300 to 1500 meters per second. So that's supersonic speeds. Now these particle sizes that are fed into the chamber, typically from 10 micron to about 100 micron, depending on the nozzle design as well as the system that is used for the cold spray process. The supersonic impact of the particles generally leads to severe plastic deformation of the particles, which then interlocks with the particles coming from subsequent deposition. And this creates a unique metallurgical bond on the particles in solid state. So there is no melting that is taking place of the metal or ceramic particles, and these is directly delivered onto a substrate plate without melting the particles. So let's look at different additive manufacturing processes and compare where cold spray process stands with regards to the other process. Now, on the right-hand side, where we need high feature resolution, that is complex shapes, geometries, highly tolerant geometric designs can be fabricated using electron beam powder bed fusion process, as well as laser powder bed fusion process, which is the SLM. But looking at the drawback of this type of additive manufacturing processes, the build or deposition rate for these processes is very slow. So it's quite tedious to generate a decent size of a component using these powder-based fusion techniques. When we compromise on the feature resolution and want to have a better build deposition rates, other techniques that are available is ultrasonic assisted machining or ultrasonic additive manufacturing, where casting can take place ultrasonically in the chamber, layer by layer, as well as laser welding DED and laser wire DED and laser powder DED process. So these techniques have better deposition or build rates, and the drawback is the feature resolution is not that unique. So it would definitely require some sort of machining post-processing to eventually realize the geometry of the final product. Towards the end of the spectrum where we need really high deposition rates, cold spray additive manufacturing is one of the top-rated additive manufacturing techniques, which can print parts up to several meters in a few minutes to up to an hour. So that's very high with regards to the additive manufacturing technology. Compared with the friction stir welding deposition, which is also suited to low melting point materials and can be delivered or deposited at a very high rate. However, the features of these components is very rough. So the surface roughness is very high, thereby requiring some sort of post-processing and machining to realize the final geometry of the component. Looking at the different features or the characteristics of cold spray additive manufacturing, the powder feed mode is direct deposition. So the powders are delivered directly through the nozzle onto a substrate plate where either the coatings or 3D self-standing parts can be formed. So it's a very unique way of direct deposition. The feedstock limitations is there is difficulty of processing high hardness and strength materials. So cold spray process is generally suited to materials which can plastically deform under supersonic speeds. So when the kinetic energy is sufficient enough for the particles to deform, such as aluminum, copper, magnesium, zinc, these materials are suited to cold spray printing. Other materials which are hard, like tungsten, carbides, ceramics, generally are limited in applications and have difficulties during processing using the cold spray technique. So powder melting. So initial raw material is the powder. However, when it's deposited or during deposition, there is no melting that is taking place. So there is no much significant changes in the metallurgy of the powder particle upon deposition, except the periphery of each of the particle, which I'll go in depth in the next few slides. The product size for cold spray technology, because it's an open chamber printing, not a closed chamber printing, the product size can be large and not limited to several millimeters to half a meter component, which is generally the case with powder bed fusion techniques. So that's a plus point for cold spray additive manufacturing. The dimensional accuracy is very low, as I mentioned, and therefore it requires a lot of post-processing to come to the final part dimensions. The mechanical properties of the as fabricated or as sprayed component is very low as well. Now, this I'll discuss in my first case study for today, why as to the as sprayed properties are low and what can be done to improve these properties. So to improve the properties, some sort of post-heat treatment is required, which can drastically improve the strength and the hardness of the cold sprayed components. The production time, as I mentioned, is quite short compared to other additive manufacturing techniques. So that's a plus point. Equipment flexibility, because it's an open chamber, it can use a robot system with 6-axis degrees of freedom. So there is much more flexibility for the equipment as a whole. And it is also suitable for repair. And not many other applications are suitable for repair in the additive manufacturing sector. Compared to coating process, how does cold spray process compare with other plasma-based or heat-based techniques? So the other coating techniques involves high energy plasma spray or the plasma spray, as well as the high velocity oxy-fuel sprays. Now, all of these coating techniques involve high temperatures that are generated for the powders that are fed into the system, and those are subsequently sometimes molten in state upon deposition. This results in significant property changes from the raw material stock itself to the coatings. Cold spray, on the other hand, as the name suggests, it has low temperature. So the temperatures are generated is less than 900 Kelvin. And generally, the particle velocity that is executed during the process is about roughly 300 to 1500 meter per second. So compared to the different type of coating process, cold spray process has low temperature, so low energy is going into the system. Thereby, we would require low pressure gases as well, and the temperature to generate a final product. Let's look at the system itself. The cold spray process consists of 5 different systems of 5 different components. One is the powder feed line, where the powders, typical size of 5 to 15 microns, are fed at a rate of up to 18 kilograms per hour through these nozzles. This powder is then fed through the feed lines to the chamber, where the powder is heated up to a certain temperature. On the other side of the system, there are gases that are delivered to the chamber as well. And these gases are heated to a certain temperature and can be, up to 1000 degrees centigrade. And the pressure at which these powders are delivered to the chamber is up to 50 bar. Using the temperature of the gas and the high velocity at which the gas is fed into the chamber, the powders get heated up instantly and are then delivered through the cold spray nozzle at a very high speed. So the 5 components that we are looking at is the powder feeding system, the gas heating and the gas delivery system, the actual nozzle, and the deposition area. A typical example of how a cold spray nozzle looks like, chamber looks like, is this is the chamber where you have the powder feed line coming at the bottom over here. Powder is fed into the area where gases are fed at high temperature and pressure, and that gas carries the powder through this nozzle and is then ejected from the end of the nozzle. Based on the pressure at which the gas is fed into the chamber, the process can be classified as high pressure cold spray system or a low pressure cold spray system. So for high pressure cold spray system, generally the pressure at which the gas, which is compressed gas, nitrogen, helium, or compressed air, is fed into the chamber is about 1 megapascal, whereas any gas system that is fed at low pressures, less than 1 megapascal, is classified as low pressure cold spray system. Let's look at the different parameters that are involved in determining the efficiency and the optimization of the cold spray process. So the powder is fed into the chamber over here. The main factor that determines the characteristics would be powder feed rate, how fast the powder is fed into the chamber and how fast is it delivered onto the substrate plate. Then the gas pressure, gas temperature, and the type of gas, and the speed with which the nozzle travels along the coating line or the deposition line, and the distance from the nozzle to the substrate. So these are the main parameters that determine the characteristics or properties of the deposit. Within the deposit, the other parameters that needs to be considered is the scanning step. So the distance between one layer of deposit to the next layer of deposit is known as the scanning step. The larger the step, the more less dense the deposit is. So this scanning step needs to be optimized to realize highly dense coatings onto the substrate plate. Then the spray angle. So if the substrate plate or the spray nozzle is delivering the powders at different angles, it can also generate different characteristics on the surface of the deposit, and this will be discussed later during today's talk. So broader picture, yes, there are a lot of parameters that needs to be considered for gas injection system, such as pressure and the temperature at which it is fed, the particles injection system, so how much volume of the particles goes into the nozzle and how much volume of particles is coming out of the system, and that is then controlled using the nozzle itself. So the converging part of the nozzle with respect to the diverging part of the nozzle determines what will be the input velocity of the gas and the particles and the ejection velocity of the powders towards the other end, and the distance between the nozzle and the substrate plate itself. Within the gas, again, there are different thermal properties that needs to be considered and thermal properties for the particles that needs to be considered to figure out what exactly the pressure and the temperature required for that material system to be deposited onto the substrate. For the deposit, the general adhesion conditions is the substrate plate should have a very smooth surface finish. So if the surface finish is smooth, there is a possibility that all these particles bombard onto the substrate and then stick or adhere onto the surface itself. If there are roughened surfaces, there is a chance that there will be more absorption of these particles onto the surface, thereby creating highly porous coatings. The best case scenario is to have a textured type of substrate plate where regions that are grooved acts like an absorbing media on the substrate where the particles get deposited into this region at a sufficient rate, whereas the other side of the grooves, which is ejecting out of the substrate plate, they act as the platform for reducing the rebound of the particles from the coating itself. So what are the different stages involved in the cold spray process? There are 4 different stages. First is the addition of the first layer. As soon as the first volume of powder particles is bombarded onto our substrate plate, stage 1 is how improved is that adhesion, that bonding between the first layer of metal powder particles onto the substrate. If the bonding is not that good, then automatically the subsequent deposition metal powders will peel away the first layer and the part will fall off from the substrate plate. Once we establish a really good bonded first layer, then the next stage is to identify the particle deformation velocity, that is the critical velocity to keep these particles sticking onto the layers that are deposited one upon the other, and as well as to realign so as to get different shapes of the component during deposition. Then the third stage is to increase the particle bonding, not just on the top layers that are getting printed, whereas the bottom layers where the porosity or the voids can be reduced further down to improve the bonding between the first several layers of deposit with the next layer of deposit. The last stage is where further deformation is required by adding sacrificial layers on the top surface of the deposit of the part itself, where this is highly porous on the top surface, and the bottom region, which is the actual component, will have highly dense features in the part itself. So looking at the process kinetics, you can clearly see that there is no melting that is taking place. So this is purely a solid state material deposition process, and it relies purely on the kinetic energy of these particles that are being bombarded onto the substrate, and as well as the previously layered coatings. With the impact of these powder particles on the substrate and the deposited layers, there is a slight amount of heat energy that is generated during the plastic deformation of the particles. And this is responsible for further increasing the bonding between the particles itself. The resulting cold spray microstructure is highly dependent on the process parameters, as we discussed in the previous slide. From the formation of interlocked particles from the first layer to the next few layers of deposit to severely damaged particle splats. So in the last stage over here, you can see that these particles that are generally plastically deformed, known as splats, are severely deformed. Nonetheless, one of the drawbacks of cold spray process is there will always be porosity involved in the component, but this can be reduced by post-heat treatment. At Swinburne, we have the most advanced cold spray machine, that is light speed 2D machine. Dimensions of the part that can be printed is about 350 by 300 part. And the maximum weight of the part that the robot arm can hold is up to 4 kilos. It has, excuse me, it has an integrated powder system which is fed into from this door, and the powder feed lines deliver the powder from the bottom of the cold spray system. And in the next slide, I'll show you exactly how the different components of this light speed 3D machine work and what is achievable. So in the powder feeding system, that's the closed door that I was showing you on that picture. We have the powder feeding open feed area, the top one, and there is a thermocouple over here to heat the powders to a certain temperature up to a maximum of 550 degrees centigrade. Then this powder is fed into the feed lines that directly goes to the bottom of the cold spray chamber and is delivered through the cold spray nozzle. Now, this is delivered onto a substrate plate which is connected to the end effector of a 6-axis robot arm. So there is a high flexibility of this robot arm to tilt the substrate plate in different orientations to exercise the print or part dimensions and the geometry of the print part. The compressed air comes from another room where it is compressed in the tank at about 30 bar and is fed into the heating unit that is separate and then comes directly to the chamber, to the nozzle, helping the particles to supersonically speed up and be deposited onto the substrate plate. So this was all about the systems and the cold spray fundamentals. Now my talk involves different case studies of coatings as well as 3D additively manufactured components and the properties of these parts. So the first study is the effect of build orientation and post-build heat treatment on the mechanical properties of cold spray additively manufactured copper, which is pure copper. The gas, again, as mentioned, is compressed air. We use 30 bar pressure, which is 3 megapascals, so it's a high pressure delivery system. And the gas temperature that is used to heat the powders is about 425 degrees centigrade. The copper parts, the pure copper parts, are printed in two different orientations. This block over here is known as the XY or the horizontal block. And we have a Z block, which is the vertical block, printed exactly with the same dimensions. To compare the properties of the different features of the cold spray parts, we wanted to see how the part performs in as deposited state in both XY condition and Z condition, as well as then heat treated to different temperatures. We selected 400 degrees Celsius as the annealing temperature, because at that temperature, copper particles or the structure recrystallizes quite significantly. So we wanted to see what will happen to the mechanical properties of the parts in two different orientations if it is just about recrystallized. And then the next heat treatment was selected at about 1000 degrees centigrade for about 1 hour. The reason for selecting such a high temperature is to go as close as possible to the melting temperature of copper, such that each individual particle then can sinter properly with each other and increase the metallurgical bonding between the particles and subsequently reduce the porosity if possible. And all of these mechanical properties were compared with the wrought as received plate. Looking at the mechanical properties, let's look at the hardness of the components. The hardness of the as deposited materials in both XY and Z was significantly higher than that of the wrought material, which is about 100 HV. And that we get from the as deposited rate is about 120 to 130 HV. With further heat treatment of the as deposited part at 400 degrees centigrade, what we realized is the hardness of the part decreased quite considerably. And it went down to about 75 HV, where we were not exactly sure what's happening there to reduce the hardness. Then with further treatment at 1000 degrees centigrade for the two different orientations, the hardness further reduced to less than 50 HV, which was not the goal for this study. What we then did is tested this under tensile loading and wanted to figure out what's happening with the different post heat treatments carried out on the as deposit part. For the wrought copper part, what we realized is the mechanical strength, the ultimate tensile strength, and the fracture strain, that's the ductility of the parts, is quite high because it is a cast product, conventionally fabricated and rolled, so it will obviously exhibit very high mechanical properties. In the as deposit state, what we found was the ductility was quite low. It's because the parts were mechanically interlocked, not metallurgically bonded at that state. The strength levels is about half that of the wrought material, about 125 to 150 megapascals. With heat treatment at 400 degrees Celsius, we found that the strength considerably increases, as opposed to the hardness data that we saw, where the hardness reduced with the increase in temperature for heat treatment. For 1000 degrees centigrade in both XY and Z components, what we found is the strength reduced compared to the 400 degrees centigrade, and the ductility also reduced. To explain this phenomena, you can see in this graph, we do not have the Z components that were tested for as deposited and the 400 degrees centigrade, is because when we were trying to machine tensile coupons out of the 3D printed Z blocks, they started to fail quite significantly, and we could not achieve the desired number of tensile components to establish a Z repeatability of the components in both as deposited and heat treated conditions. When we treated to 1000, fortunately, what we had or what we observed is these cracks were considerably reduced, and we were able to extract at least 3 to 5 tensile coupons to test. What exactly is differing in these three conditions that results in such diverse reaction to the mechanical testing in both hardness and tensile testing? Looking at the microstructure characteristics of these parts, the as deposit state, you can see the individual powder particles can clearly identified, and those are quite severely deformed, forming planar type of particles, powder particles. More kind of these particles have porosity, or the boundaries are clearly established in both the XY and the Z components. For the 400 degrees centigrade treated samples in the XY and the Z parts, what we observed is this grain structure is quite significantly modified and refined, and the grain size is quite fine, up to about 3 to 5 microns compared to about 20 to 25 microns that of the as received powder particles. Following 1000 degrees sinter treatment, what we observed is there was not just recrystallization but significant grain growth, resulting in large grains that were formed, more than the 25 microns of that of the as received powder particles. But what we also observed is there was coalescence of the porosities, forming gross porosities all throughout the components. So we have large porosities that were formed in the parts itself. Now, looking closely at the SEM microstructures of these components, what we observed is in the as deposit state, because of the severe plastic deformation of the copper powder itself, these particles had intra-grain particle fracture. So the particles themselves showed significant signs of fracture and failure within the splats itself, compared to the interparticle fracture, where the boundaries between two or three different powder particles shows some sort of gap, as though it's not bonded well together, rather just attached or stuck together because of locking with other particles beside them. At 400 degrees centigrade, although in the optical microscope images, we cannot see anything significant apart from the refinement of the grain size itself, but under the SEM, we could clearly see that there were a vast network of pores and gaps that were formed along or in between the refined grains itself. And this is the reason why the hardness of these components, although is reduced quite low, is because there is fractured particles and porosities that are embedded into the interparticle refinement of the grains itself. Thereby, the hardness is quite low. When tested in tensile, these network of cracks and pores resulted in quite low ductility, but because of the refinement, there was an increase in strength. So the objective is now to reduce these porosities and maintain the strength of the refinement of the copper particles itself. At 1000 degrees centigrade, we could clearly see that the particles or the grains have grown quite largely, and there are intergranular pores and defects that, although not well connected to each other, can result in areas for the cracks to propagate quite rapidly. Thereby, if we looked at the hardness profile, the hardness was quite low because there were a lot of porosities and defects in the component itself, which resulted in low hardness as well as low strength in the part compared to the 400 degrees Celsius heat treated refined structure of the copper block. We then also did XRD analysis just to see if there is any differences in the elemental composition of pure copper. Although the heat treatment was done in a muffle furnace, so we thought there might be some sort of reaction to oxygen that might happen, or there is oxygen in the as received powder particles that can result in oxides forming in these gaps, which cannot be removed by post heat treatment. Looking at the XRD data over here, clearly we had all the copper phases, and that's the 111 and the 200 alpha phase, and we had a slight bit of copper oxides that were formed. The contents of copper oxide was quite high in the powder, which was about 6.7 weight%, and this is on the periphery of the powder particles as we expected, because the copper powders were gas atomized, and there was a huge chance that it can absorb oxygen from the atomizing chamber within the atomizing chamber if there is any leakage of oxygen. In the as printed state, the copper oxides decreased quite significantly. So what we observed is the powder, although it contains huge amount of proportion of oxides on the periphery, once deposited, these oxides are very minimal compared to the subsequent plastically deformed splats that are formed for copper. With increase in temperature during post-heat treatment, there was an increase in the oxide level itself, because each individual copper particle, as well as these pores and defects, had entrapped oxides in them and absorbed this into the structure itself. And with 1000 degrees treatment, this further increased to about 2 weight%. For the fracture surface analysis, we did both X, Y, and Z for as deposited and heat treated conditions. What we found is the fracture happened along the interparticular boundary, where the particles were just mechanically interlocking rather than bonding together. So this is quite evident from the Z block over here, which we could not test under tensile loading, that the particles quite abruptly fail where there is not enough bonding between the deposition. In the anneal state, this fracture, although quite abrupt and sharp, there was some sort of ductile failure pattern that was observed from the intraparticle failure fracture pattern. And likewise, in the Z direction, we had the cracks propagating along the porosity network, thereby resulting in very abrupt failure of the parts. In the 1000 degrees centigrade treated components, the gross porosities or defects that are formed results in quite abrupt failure of the component itself. Looking at the morphology of the surface, the fracture surface, the as deposit state consists of cleavage type of fracture, very abrupt, clearly showing that the particles are not well bonded and they're just being pulled apart during the tensile testing. For the post-heat treated sample, there are ductile regions as noticeable because of the refinement of the grain structure, thereby increasing the strength as well as ductility of the component. In the 1000 degrees heat treated component, although we had more kind of ductile dimple-like features observed on the component, but there were gross porosities such as these huge gaps that resulted in very fast fracture and low ductility of the components. So the ideal goal for cold spray process for copper deposition would be to establish a ductile type of failure pattern across the entire part without the gross porosities that are observed in the high heat treated samples.
Excuse me, Dr. Rizwan, maybe we still have 3 minutes more before discussion.
Oh, okay.
Thank you very much. Okay, or maybe 5 minutes, I think.
Okay. So what I'll do, I'll just quickly run through one more slide, and then I'll go to the last few slides.
Oh, okay.
So the effect of spray. Thank you. So the different parameters that we studied during the study was the effect of spray angle. When the core of the samples were printed, they were printed at a 90-degree deposition angle, whereas edges of the sample were printed at a 45-degree angle. Thereby, this change in the spray angle created a huge network of porosities in the component itself. Thereby, for the Z block, which is a high block, have huge edges or huge amount of edges on the sides, resulted in highly porous network and low tensile and mechanical strength. So this study over here was more kind of similar type of study compared with aluminum 6061 rather than copper. We found the same sort of porosity distribution across the as deposited horizontal sample and the heat treated samples, where the porosity was quite significant in all orientations that we studied. With subsequent heat treatment, although what we observed was the porosity is decreased compared to the as deposit state, which is the main intention of the post-heat treatment. After heat treatment, what we observed is the ultimate tensile strength and the hardness increased quite drastically compared with the as deposit state, and the ductility also increased quite or improved quite better compared with the as deposit state. So aluminum 6061 or aluminum based alloys were quite suitable or favorable for cold spray deposition using this process compared to the copper powders. So sorry about that. I'll just skip to this main coatings application that I wanted to discuss. Is we also did one study where we coated existing door handles, door knobs with copper, because copper has high antimicrobial resistance characteristics, and for which we wanted to see if this can fight against COVID-19, or that is during the coronavirus pandemic that happened. We wanted to see whether it's possible to establish this type of idea. So we used existing door handles, door knobs, and push plates that were available for us. We coated with a thin layer of copper coating, about 0.7 millimeter thick, and the spray just took about 7 minutes. So just taking the plate from the door, fitting onto the substrate plate or the end effector of the robot arm, using a program to just deposit 0.7 millimeters thick coating, and 15 minutes back onto the door itself. So this was highly popularized, you can say, in Australia, and there were techniques to consider this to use this for other applications as well. So looking at the effect of copper in killing the coronavirus, what we observed is in the as deposit state, copper had a very good killing ability, whereas in the anneal state, the copper could not be as effective as the as deposit state. And this is because these coronavirus bacteria, or the microbes, require some sort of ions that that can interact with the cell wall, damage the cell wall, and thereby reduce its efficacy and be killed on the surface itself instantly. So this study clearly identifies, okay, apart from the paper and tissue, which needs 3 hours to kill the coronavirus bacteria or coronavirus microbe, copper is the next best material available to rapidly kill this bacteria, this microbe. And this was also observed using other bacteria, that is E. coli and S. aureus. Now, the key takeaway from this talk was to identify, okay, cold spray additive manufacturing is now evolving from just a coatings process to an additively manufactured process, but there are other parameters that needs to be considered to establish a fully printed component and be put into service. So for the CSAM parts, machine and process parameters need to be significantly optimized before the part can be printed, and the part itself needs to be optimized in design, which can be printed using a cold spray process. These parts are to be heavily tested and characterized, and this testing data should be fed into a materials database, thereby giving finite element simulation modules or the modeling software's ability to understand and simulate the characteristics of the component that is printed using a cold spray process. Thank you very much. I hope it was interesting and I can get some questions now. Thank you.
Okay, thank you very much, Professor Rizwan, for the interesting and inspiring talks. It's about cold spray process additive manufacturing, and it's quite maybe new technique also in additive manufacturing. Okay, Bapak Ibu partisipan, I invite if there are some questions or comments about Dr. Rizwan talks today, please, you can raise hand or just write in the chat box. Okay, I'll maybe start some question, Dr. Rashid. Okay, it's the cold spray process additive manufacturing is so not involve the melting of the powder, yes, the feeding powder. So instead, it's heat the gas for the process. Yes, it's right. So, but so it's so called the cold spray process. So cold spray process. So I'd like to know about how complex the substrate shape, the form of substrate that can be applied for the spraying process, the cold spray process here. Could you maybe explain? It's very how complex, maybe. Yes, such maybe example for the simple one and the most complex ones like that.
Yeah, sure. Thank you, Dr. Albertus. So with regards to the complexity of the part that can be used as a substrate, it all depends on the degrees of freedom that is available on the system itself. So this cold spray machine that we have, it's 6 degrees of freedom, and it's connected to an end effector. So effectively what we can do, if we have a component which is very complex, we can scan the part, laser scan the part, convert that into a CAD file, and use that as a substrate module to deposit on the substrate itself. So the part itself can rotate on the end effector in whatever orientation we want it to deposit, and we'll have a good deposit. Coming to a question of complexity, yes, there will be a limitation as to how deep the powder can penetrate on the part itself. So if you have a part that has an embedded feature, inherent feature, it cannot go too deep to deposit the powders, or there is not enough kinetic energy for the powders to adhere to those non-available or non-reaching spots on the part. And the simplest of parts would be any part. You can take a door handle, say, for example, that's quite easy to use, and you can directly deposit on top of it. Sorry, you're on mute.
Sorry. Thank you very much for the response of my question. Oh, okay, we have a question from Bapak Inyuman Jujur.
Yep.
Okay, I will read the question. Interesting about cold spray AM. My question is, in terms of equipment prices compared to electron beam melting or laser, which one is more expensive? The cold spray process requires a heat treatment process, whereas for EBM or laser, does not require it. Is it true? And then, is there any information about research in the field of biocompatible materials using cold spray AM? Okay, maybe you can respond this answer, the question, Dr. Rizwan.
Yeah, sure, no problem. Thank you. Thank you for the question. Now, I see in your message, Juju, you have three specific questions that you're asking. First one, compared to the laser and electron beam melting machines or equipment, whether cold spray machine is expensive. No, cold spray machine is not that expensive. It just involves a robot arm. You have the powder feed lines, which is also used in other additive manufacturing processes. However, electron and laser beam is quite expensive because it needs to deliver a certain type of energy, that is the heat source, in terms of laser and electron. For electron beam melting, general prices is more than $1 million Australian dollars. Laser-based systems starts from about $750,000 onwards, and cold spray machine starts to about $600,000 Australian dollars. So in terms of cost or economics of the machine, cold spray machine is much more affordable than other additive manufactured machines. Looking at the second question, yes, heat treatment is involved for cold spray as well as the other AM processes. Now, how would I describe this? In electron beam melting or laser beam melting processes, you are rapidly melting the powder particles and solidifying it quite rapidly as well. So the structure in more kind of metals is martensitic structure, which is non-equilibrium. Thereby, it does not show really high properties and requires subsequent post-heat treatment to establish or bring out the actual strength of the component. So in terms of heat treatment, yes, all processes require post-heat treatment to get the tailored suit of mechanical properties for that component. Last question, is there any information for research in the field of biocompatible materials? Yes, titanium is one such type of material that is used in the cold spray machine to deliver a 3D component. But titanium, although it's biocompatible, the titanium components that are formed from cold spray has porosities in it. So if they are used as biomedical implants, these porosities will act as channels for the biological fluids in the body, human body, to penetrate and damage the implant itself. So subsequent research is needed to identify the niche area to use titanium or other biocompatible materials that are cold spray additively manufactured for implant or other subsequent biomedical applications.
Okay, thank you very much.
Thank you.
Professor Nyoman Jujur, how it's I hope the response is answered your questions.
Yes,
now
it's okay. Thank you.
Okay, thank you very much.
Thank you very much,
Professor Nyoman Jujur.
Yeah.
Okay, we have maybe three questions here. First, I'd like to invite Dr. Muyunan Hasbi, there, which is raising his hand.
Okay, Mr. Denny, thank you very much. Assalamualaikum, Mr. Rizwan.
Walaikum salam.
Okay, my name is Yunan. I'm from Research Center for Metallurgy. I want to ask some question. And first question is there a limit to the materials that can be processed with this technique? Since cold spray coating works at low temperatures and low speed compared to other previously available coating techniques, such as plasma coating and HVOF spray. And the second one is there any requirements for powder specifications such as particle size or shape or others? Thank you very much.
Thank you very much for your questions. Yes, the cold spray materials, the materials that can be used for cold spray, they need to be highly ductile, that can plastically deformed upon supersonic speeds, upon deposition. And also it depends on the system itself. So if we have a high pressure system, the materials like hard materials like stainless steels, even tungsten can be deposited using the cold spray machine. But for low pressure systems, which has less than 1 megapascals pressure of the gas, the materials are very limited. So at this point of time, we are trying to evolve this process for coating or depositing hard materials. Your next question was on powder particle size and the shape that is used for this process. In one of the studies that I wanted to talk about, we used powder particles that were irregular in shape. So if I may, I'll quickly go back to just the slide, just to show how irregular shape these powders were. So these powders were not spherical in shape, and they ranged from 10 micron up to about 100 microns in size. There was difficulty for us to use the existing cold spray machine to print these parts. What we needed to do is to pre-heat treat the powders itself to reduce the residual stresses in the powders to make it coatable or depositable in this case. And we were able to achieve that by heating this aluminum 7075 powder particles at 300 degrees centigrade for about 4 hours. And we could get a nicely deposited structure. I hope I have answered your questions.
Okay, thank you, Mr. Rizwan, for the answer.
Thank you.
Thank you, Mr. Denny.
Okay, thank you, Dr. Muhyonan, for the question. Now is, I think, one more question, I think, from the chat box. This is from Dr. Iwan Setiadi from Green. Given the limitation of CSIM, is it not always possible to make precision component and still get porosity? How to create complex shape with CSAM? Is it helped by using mold or just to make a thin layer only? What is specific application? And maybe there is a video describe the process. Maybe please probably respond to the question, Dr. Rizwan.
Sure, no problem. Thank you so much for the questions, Dr. Satyadi. Now, coming to your first question, how to create complex shapes using CSM. So CSM is not a widely applicable process. So you cannot print inherent internal features for the parts as you can do for electron beam melting or other laser-based processes. So CSM is a niche technique only applicable to certain components, not every component. Even though we have, as I explained in the first question, we can use existing substrates or molds to deposit it on top of these molds and substrates to generate complex shapes. But that's the only limit we have. If we need an internal feature like a cooling channel built into the copper plate, this is very difficult to achieve using a cold spray process. Coming to the next question, is there any video that describes the process? Yes, we have a lot of videos. Sorry, I could not incorporate that in today's slide. But if you do pass me your email address, I will send you links to a couple of videos that we have.
Okay. Okay, thank you very much. I think.
Thank you, Mr. Rizwan. Thank you very much.
Yes, thank you, Dr. Iwan Setiadi. I'm sorry, but the time is limited now because we also start about delay time. So if you, Bapak Ibu, if you still have a question or any maybe in the future collaboration work with Dr. Rizwan, I think you can send an email to Dr. Rizwan Abdurrahman Rashid. Or
More
maybe,
than welcome.
Yes, thank you very much.
Thank you very much.
Rizwan. So let's applause our speaker today, Dr. Rizwan Rashid from Swinburne University of Technology. Thank you.
Thank you. Thank you so much.
Okay, next. Now we move to the second plenary session. I hope Professor Zaki Mubarak is available. Oh, yes, Professor Zaki Mubarak is available here. Yes, the second plenary session will be delivered by Professor Dr. Zaki Mubarak from Department of Mining and Petroleum Engineering at Institute Technology Bandung. Now I'd like to introduce a brief introduction about Professor Zaki Mubarak. Professor Dr. Zaki Mubarak is a professor and faculty member of the Metallurgical Engineering Study Program at the Department of Mining and Petroleum Engineering, Institute of Technology Bandung. He obtained his bachelor and master degree in engineering from ITB and a PhD from University of Leuven, Austria. He also obtained the professional degree as engineer from ITB. Professor Mubarak has long and extensive experiences in teaching and academic services. That is serving as a lecturer in the Department of Mining and Petroleum Engineering, ITB, from 1999 to now, doing a postdoctoral fellow at University of Leuven, Austria in 2006, 2007, as a head and manager of Hydrometallurgy Lab, the head of Metallurgy Engineering Study Program, a professor in extraction metallurgy since 2019, and now is a deputy of dean in Sekolah Parsar Sarjana or postgraduate school at ITB since 2020. Professor Zaki Mubarak has a solid track record in research on extraction metallurgy. In recent 10 years, he has been a principal investigator and team member and in a number of research projects, including the refining of nickel cobalt hydroxide for raw materials of NMC battery, development of natural mineral extraction for lithium battery, and so on. Professor Mubarak has published in more than 40 international and national journals and delivered more than 55 talks in international and national seminar or conference, including those as a keynote and invited speaker. He has patent granted and received numbers of awards, including high equation scientific paper awards from Kemenristek BRIN, Mining Mineral Industry Institute Research Board from Mine ID, ISMM Best Paper, and Satya Lencana Pengabdian for the Government of Indonesia. Professor Mubarak is also active in professional, community, and society services by engaging in more than 25 projects of consultancy and expertise services, collaborating with renowned mining industry in Indonesia. And today, Professor Zaki Mubarak will deliver a talk entitled Extraction of Nickel, Cobalt, and Scandium from Indonesian Limonite Ore by High Pressure Acid Leaching. Okay, Professor Zaki Mubarak, good morning.
Good morning, Pak Denny.
Yes.
Thank you very much for the introductions.
Yes, thank you. Now I think it's time for your talks. I will give the time and screen for you now. Please, the time and screen are yours.
All right, ladies and gentlemen, in these occasions, I would like to deliver a presentation entitled Extraction of Nickel, Cobalt, and Scandium from Indonesian Limonite Ore by High Pressure Acid Leaching. First of all, I would like to thank the ISMM organizing committee that has invited me to deliver these presentations. Okay, I would like to deliver a talk following this outline, started with introductions, talking about the development of nickel laterite processings and some recent progress in Indonesia. And then I would like to share research that have been done by our group at ITB and the investigation results and discussions. And I'll close the presentation with concluding remarks. As an introduction, as perhaps you have been aware that low-grade lateritic nickel ore of limonite type has not yet been significantly or extensively processed domestically. Since a very long time, we only treat saprolite, the higher grade of nickel laterite ore, for producing ferronickel, nickel pig iron, and nickel matte. Just in the last 2 years, 2021, the commercial operations of hydrometallurgical plant started commercial operations that treat limonite ore, and this year the other one is also starting their commercial production. Despite the lower grade of nickel, limonite ore has relatively higher content of cobalt and scandium than saprolite. Now and soon, nickel and cobalt demand is or will be growing rapidly due to the electric vehicle industry's growth that requires this metal for its batteries. And why choosing the nickel-based battery is because nickel-based battery has higher specific energy density in comparison to, say, cobalt-based or lithium iron phosphate. In this context, the extractions and purification technology of nickel and cobalt from limonite ore is urgent to be domestically developed, especially for producing battery precursor material. And this is the illustrations how the ore must be extracted and purified to produce nickel sulfate as a raw material of cathode precursor that further processed to produce battery cells for the electric vehicles. Well, in this slide, prediction of nickel-based and other type of EV batteries market and nickel demand for EV. In the left picture, you can see that now and in the future, nickel manganese cobalt is the battery type which is dominant until 2040. And on the right picture, you can see that the growth of nickel demand for batteries is consistently increased in the next 20 years, until 2040, which is around 2,750,000 nickel equivalents. Okay, and Indonesian nickel mine reserve and productions at the moment, we are is the largest country with nickel production and reserve, and this is since 2017 until last year. I think this year is also. I put the data from US Geological Survey, Mineral Commodity Summaries, January 2022, that we produce 1 million nickel equivalents, in various forms, mostly in the form of nickel pig iron. And our reserve, according to this USGS, is reported last year, 2,001 million ton nickel equivalent, similar with Australia in this picture. But this number is actually has not considered the lower grade or limonite type. If it is calculated according to our Indonesian Ministry of Energy and Mineral Resources, the nickel reserve equivalent is about 50 million, and even higher, just recently. Limonite ore, as already mentioned, having higher cobalt than saprolite ore, and in addition, besides as a primary source of nickel and cobalt, lateritic ore are also known to contain rare earth elements, one of which is scandium, that I would like to talk today. Scandium is currently the most valuable rare earth element in laterite ore, and the price of pure scandium oxide this year is $2,200 USD, not per ton, but per kilogram. And some various type of product are more expensive. And in the form of scandium ingots, is much more expensive 137,000 USD per kilogram. This is according also to USGS Mineral Commodity Summaries, January 2022. Scandium is used in advanced and strategic application, such as an alloying element in aluminum scandium alloys for constructing the fighter aircraft. Actually, the scandium percentage is only in the range of 0.2 to 0.8%, which contribute to the improvement of mechanical properties, corrosion resistance, and the wettability. With potential strategic application and high values, the process of extracting scandium from domestic laterite ore is urgently required. And in fact, commercial production of scandium oxide, SC2O3, as byproduct of HPAL plant has been done in 2 HPAL plant in Philippines and in Indonesia. I have not seen this plant, and actually it is important to recover scandium from laterite ore. And talking about technologies for nickel laterite ore processing, perhaps most of you or part of you familiar. This processes ferronickel smelting, mid smelting, nickel pig iron, cupran, lupen, which are belong to pyrometallurgical processes. And then Caron process, the combination of pyro and hydrometallurgical process. And then high pressure acid leaching, which I want to discuss today. Atmospheric agitation leaching, heap leaching, and other technologies such as direct nickel, which belong to hydrometallurgical processes. Of course, this process has advantages and disadvantages. And in terms of comparisons, emission of CO2 from various nickel processing technologies, it can be seen here. If we talk laterite ore, that HPAL process produce CO2 emission, which is significantly lower than rotary kiln electric furnace process, as well as NPI process, which are both produced by RKEF. And we cannot compare with sulfide ore. Sulfide ore is much lower because the processing does not involving the reduction of oxide that generate the CO2 gas, CO and CO2 gas. And this CO2 emissions, low CO2 emission to produce class 1 nickel for battery material is a critical issue, because we want to have a green application of transportations. But if we produce on the downstream, on the upstream, the emission of CO2, then it doesn't make any sense. So it's important for realizing low carbon economy and environmental, social, government, or ESG aspect. And if we talk about the hydrometallurgical technology processing for limonite ore, there are some technologies, as already mentioned: Caron, HPAL, atmospheric agitation leaching or AL, heap leaching or HL, and others. And there is no new investment for the Caron process due to recovery level of nickel and cobalt, which is low, in comparison to HPAL. And then investment costs or CapEx and operating costs, which are considered to be no longer competitive. HPAL technology is considered as a reliable and proven technology, which has been used in most of hydrometallurgical plants worldwide for treating limonite ore. This is what happened in industry, but we just started, and it's important to make a study to confirm, to find the critical issues at laboratory scale, at research scale. So basically, high pressure acid leaching is leaching of nickel, cobalt, as well as scandium. at temperature of 240 to 270 and pressure of 33 to 55 atm, and the leaching agent is sulfuric acid. It's done in a reactor called autoclave. And the excellence of HPAL process is the recovery level of nickel of cobalt quite high, as well as cadmium. I would like to show to you today. And the process is quite quick. It's only about 1 hour in comparison to atmospheric agitation leaching or heap leaching. It is much faster. And the most remarkable excellence of HPAL technology is the leaching is selective to iron. It means that co-dissolved iron is hydrolysis as non-soluble hematite during leaching. These are the mechanism of nickel and cobalt dissolution, as well as iron dissolution from limonite ore. So if we want to dissolve nickel from limonite ore, we have to dissolve iron. Why? Because the presence of nickel oxide is within and the metric of goethite. And the problem is how to reprecipitate the dissolved iron in order to get lower acid consumptions and more pure pregnant solution. So the dissolved iron is precipitated or hydrolyzed to form hematite according to these reactions. Okay, and this is the illustration of autoclave constructed in industry somewhere in abroad. Yeah, and in this table, each power plant that have been operating in the last 20 years and to be operated in the next 5 years are shown. Important is we look at Indonesia. We have PTHPL already started 2021, yeah, with the design capacity of around 35 ton nickel per year, yeah, in the form of MHP or mixed hydroxide precipitate, and currently it's developing the additional facility for treating MHP for producing nickel sulfate and increasing also the capacity. And the other one is Huayu, this in Morowali Industrial Park, just started also this year with final product of MHP, quite high capacity with 60,000 ton nickel equivalent in the form of MHP. And the other one is QMB, which is also developing facility for treating MHP to nickel sulfate and until battery cathode precursor materials. And the other one, Vale Sunrise. Thing that we have to give a note for the HPAL plant is the ore feed characteristic. So typical level of nickel in the feed of HPAL plant are in the range of 1 to 1.3%. Yeah, if we take a look on the HPAL plant worldwide. So it's quite low, yeah, in comparison to saprolite ore that for years we have been treating to produce NPI or ferronickel as well as nickel. Magnesium level in the ore is constant because it will increase acid consumption. Shared research results show that for every 1% or 10 kilogram per ton increase of magnesium level in the ore, the consumption of sulfuric acid increases by about 70 kilogram per ton. And in addition, the increasing acid consumption, increased magnesium level in the pregnant solutions can cause scaling problem in autoclave and related equipment. Once more is also the content of aluminum is also critical because aluminum is also dissolved and consuming acid and can cause also scaling in the form of alunite. In industrial practice, the level of Al2O3, aluminum oxide, in the ore to be processed is limited to 9%. Okay, these are the review of HPAL plant or characteristic, and I move forward to research that have been done in our laboratory or our group at ITB. So basically, we do the research from upstream to downstream, starting leaching, purification of pregnant solutions, synthesis of MHP, releaching of MHP, and purification of solution produced by MHP release, and then separation of nickel and cobalt by multiple stages solvent extraction, separation of nickel cobalt manganese by selective oxidative precipitation method using ozone gas, as well as synthesize nickel sulfate and cobalt sulfate for cathode material of an MC battery. So can be shown in this scheme, starting from ore preparation, leaching, and then neutralization for purifying the pregnant solutions, MHP precipitations and release, solvent extraction for producing nickel sulfate, cobalt sulfate, but I would not discuss this part, purification of MHP, more on leaching of nickel limonite ore, as well as the purifications to recover scandium. So scandium basically is recovered from second stage of iron precipitate. And we do also research how to recover iron from HPAL tailings. We obtain industrial tailing from a company that has been producing by HPAL process, and we try to recover iron in the form of iron phosphate, and that will be used also for battery cathode precursors. And this is a picture of laboratory activities for HPAL experiments, starting with ore sample preparations, reactor preparation, and the leaching experiment, and the view of pregnant leach solution we obtain. In addition, we have been doing also many atmospheric leaching experiments. Before we start with HPAL, we have been doing this kind of experiment, studying the effect of ore composition, etc. And we do also researches from nickel ore to battery cells in collaborations with Teaching Factory of Battery, UNS, Solo. You can see here the pictures when we visited there. So at ITB, we prepare nickel sulfate from nickel ore, nickel limonite ore. And in Solo, we prepare the cathode precursor until battery cells that have been also tested. And the capacity, charge discharge, stability, etc. The conductivity of lithium by electrochemical impedance, etc. So, we have managed to prepare battery cells, from nickel limonite ore, and now is still ongoing. Okay, and I would like to share some investigation results and discussions. So this is an example of our analysis result on chemical composition of ore sample we use from Halmahera and others. So you can see here that the content of nickel is relatively low, 1.48, with quite low magnesium content, but high content of iron and aluminum. And the XRD results detected goethite, FeOOH, and gibbsite as the most dominant minerals. So based on chemical composition analysis results with low nickel, high iron, low magnesium, and XRD analysis detected goethite as the most dominant mineral, it is confirmed that the ore sample is limonite with the scandium content of around 70 ppm. And the result of leaching experiment at high temperature and pressure is as follows. The experiment was designed by Takuchi orthogonal array and in duplicate. So in total, there have been 18 experiment, with variation of acid additions, leaching durations, temperatures, and or fraction. So, or size fraction. So we use this Taiguchi in order to simplify and to reduce the number of experiment. And we measure the extracted nickel, cobalt, iron, scandium, as well as aluminum. And on experiment number 7, from experiment number 7, we obtain the best conditions at 240 degrees centigrade, 40 bar, 1 hour, 350 kilogram sulfuric acid that give the highest extracted nickel and cobalt, around 95% for 1 hour, as well as scandium extractions, 91%, with co-extracted iron, which is very low, only 0.06%, and it is confirmed. It was confirmed that iron detected in the leach residue in the form of hematite. So what have been explained before, that dissolved iron is hydrolyzed to hematite, was confirmed here. And you can see here that important to have high temperature in order to get the sufficient or high scandium extraction. So if we do at 180, the extracted scandium is only 50%, and increase linearly until 220 and slightly increase from 220 to 240. This indicates that HPAL is more effective, in comparisons to AL in terms of the ability to extract scandium. And you can see also here the extracted iron is getting lower if you increase the temperatures. Okay, this is the result of our investigation for leaching, and we compare the extracted metal from HPAL and atmospheric pressure leaching, which was done by using 4 molar sulfuric acid. So it's not apple to apple. For HPAL we use in unit of kilogram per ton dry ore, but this is for molar at 95 degrees centigrade with the similar ore sample. And we can see here that with 4 molar, okay, nickel extraction is quite high, 95%, but cobalt is lower than HPAL. And the most remarkable is iron. So with atmospheric pressure leaching, we got 96% co-extracted iron. So this is big problem for purifications. Of course, the co-extracted iron is dependent on the acid concentrations. And magnesium cannot be solved by HPAL. The extraction is even higher than atmospheric pressure leaching. And the presence of iron is also confirmed by analysis of the leach residue. HPAL is much higher than in a residue of atmospheric pressure leaching. Okay, and I would like to move forward to purification of pregnant solution from HPAL for iron removal and scandium precipitation. The following is composition of the pregnant leach solution obtained by HPAL experiment done at 240, 300 kilogram per ton dry ore acid and 1 hour. You can see here that the concentration of iron is only 186. Even although in the ore is around 50% and nickel is only 1.5%, but in the PLS, iron is much lower than nickel, even lower than cobalt, and scandium, it is only 70 ppm. The ore, we get 200 ppm, 12 ppm in the pregnant solution, and the problem is aluminum is higher than nickel, 2,833. Why? Because we use iron with we use ore with quite high aluminum content, around 5%. So it's a critical issue also. And we have done series of experiments to precipitate iron in 2 stages with these conditions. Basically, Stage 1 was done at lower pH around 2.75, and the adjustment is by adding calcium hydroxide. And then from the second stage iron precipitate, releaching was done to redissolve scandium here with variation of time, temperatures, concentration of acid at atmospheric pressures and solid liquid ratio. And from the pregnant solution produced by releaching of iron precipitate, we did a series of solvent extraction involving extraction, scrubbing, stripping, in order to produce pure and concentrated scandium solution to be treated for recovering scandium compound in the form of scandium oxalate and then calcination to produce scandium oxide. And we do also at the moment the stripping with fluoride to produce another type of products. Okay, and basically if we make precipitations of scandium, iron, aluminium, nickel, cobalt, we back to this famous Monheim's diagram, the thermodynamic equilibrium between metal cations and its hydroxide as a function of pH. So you can see here that the line for equilibrium of scandium 3 is here. Is on the right side of Al3, Fa3, but on the left side of nickel and cobalt. So thermodynamically, scandium 3 can be precipitated from PLS without co-precipitation of nickel and cobalt by carefully adjusting pH, because the co-precipitation is not performed only by chemical mechanisms or based on thermodynamics, but also due to adsorption on the precipitate. Since the concentration of scandium is quite low, as has been explained before, dissolved scandium is precipitated with iron and aluminium. During the second stage of iron precipitation at pH of 4.75. This is the result of two-stage iron precipitations, iron and aluminium. At stage 1 was good. We got quite low co-precipitation of nickel, cobalt, and scandium, and quite high iron precipitations. And the stage 2, we got co-precipitation of nickel and cobalt quite high. It's still challenging, and at the moment we are still doing the condition with lower pH. But the co-precipitated nickel and cobalt, it's not a problem, because in industrial scale, this precipitate is releached during leaching, by using the liquor from each pulp. And if you want to treat the to extract the scandium and to treat this second state precipitate, there's no problem also, because scandium can be spirited from nickel and cobalt by using DIPA. And in this second stage iron precipitation, above 99% of scandium is precipitated, and the grade of scandium was increased in the precipitate to about 240 ppm for time, higher than initial concentrations of scandium in the ore, which is 70 ppm around. Okay, and we did also releaching experiment on the precipitate by variations of durations, temperature, acid at atmospheric pressure. So basically, scandium was easily dissolved at low temperature and short time from the precipitate using acid concentration of 75, lower than 1 molar. At low temperatures, 35 is sufficient. If you increase another metal dissolutions. And the optimum condition we obtain for scandium releaching is as follows. Leaching duration 90 minutes at 35 degrees Celsius with acid concentration 100 gram per liters. Okay, and solid liquid ratio of 0.2 gram per milliliter. And this is the data of extracted metal. Yeah, it's not selective, but we want to purify at the next stage, at the solvent extraction stage. And remember that co-dissolved iron in pregnant solution is quite low. Okay, and I
Dr.
would
Mubarak,
like to explain. Okay.
Excuse me,
Yeah,
maybe we still have 5 minutes more before the discussion.
Okay.
I'm sorry.
Okay, thank you. Thank you, Pak. I would like to continue to share our investigation result on scandium extraction from the second FeAl scandium hydroxide precipitate releaching by solvent extraction. And this is the concentration of the pregnant solution. So again, the problem is aluminum. Yeah, so we treat high content of aluminum in the ore. We got quite high. And we did a series of investigation in solvent extraction to study the effect of extractant concentration, volume ratio of organic to aqueous, initial pH of aqueous solution, and time. And we use DIPA, D2-ethyl-hexyl phosphoric acid with this structure for extraction of scandium with this mechanism. Basically, scandium is extracted to organic phase by replacing H+ ion. Okay, and these are some results of our investigation. So it can be seen that the scandium can be effectively extracted by DIPA. Yeah, we got almost complete extraction, 100% of scandium by 5% to 11% volume. And this is the separation factor. And also by varying the O/A phase ratio, we got also quite good at all variations. And our problem is how to get the selectivity to nickel, cobalt, and aluminum. So we got here, we got here the highest separation factors at O/A ratio of 1:1. Yeah. To get higher ratio of scandium concentrations to aluminum, iron, nickel, and cobalt. And the optimum parameter we obtain for extraction stage is as follows. At extractant concentration 5%, O/A ratio 1:1, initial pH 0.6, 10 minutes, with scandium extraction level of 99.7%, so almost complete. Co-extracted iron around 35, nickel around 11, cobalt similar, and aluminum 9. And the co-extracted iron can be effectively scrubbed from loaded organic by HCl formula at O/A 2.1 for 5 minutes. So this is the result of our scrubbing experiment, but aluminum is more difficult to scrub. So scrubbing percentage for aluminum is around 20%. So we are still doing the investigation to improve it because we got initial solution with high aluminum content. But in the stripping stage, aluminum can be separated from scandium. So we got around 75 stripping percentage of scandium and also quite high iron, but no problem because most iron has already been scrubbed. So the final concentrations of iron in the strip solutions is quite low. And the strip solutions need to be further purified to obtain the product with above 99% purity, and the investigation is still ongoing. So that was some of our investigation results regarding nickel cobalt extractions as well as scandium from limonite ore by using HPAL process. And we sincerely thanks MindID and Antam for providing nickel laterite ore sample, and research team members such as Professor James Wogan from Queensland, Professor Agus Purwanto, and Dr. Anton from BRIN, yeah, and some ex-students, yeah, my students, I will not mention one by one. And as conclusions, there are 5 remarks here that high pressure acid leachings give high extraction percentages of nickel and cobalt, about 95% in scandium, 91%, and was confirmed to give much higher selectivity of leaching to iron compared to atmospheric pressure leaching or AL. The formation of hematite as product of dissolved iron 3 hydrolysis was confirmed in the XRD analysis result of the HPA residue. And content of aluminum and magnesium in the ore is two critical parameters that must be anticipated to control acid consumption and obtaining the pregnant leach solution that is easier to purify, especially if we want to produce scandium. Scandium basically can be effectively recovered from HPAL, PLS by two-stage selective precipitation and release of the precipitate. Scandium recovery of about 99%, of above 99% can be obtained by leaching of iron, aluminum, scandium hydroxide using 100 gram per liter sulfuric acid at 35 degrees Celsius for 1.5 hours. Solid liquid ratio of 0.2 gram per milliliter. And the last, dissolved scandium in sulfate solution is easily extracted also by DEPA with a recovery level of above 99.9%. And separation of scandium from aluminum during solvent extraction state is a critical issue for synthesizing pure scandium compound. And co-extracted aluminum is reduced basically by lowering the pH of the PLS. So that was my presentation this morning. Thank you very much for your presentations. And I return the floor to Pak Denny. Thank you.
Okay. Okay, thank you very much, Professor Mubarak, for interesting and inspiring talks, especially for about hot topics in rare extraction of rare earth elements, including scandium. Okay, Bapak Ibu, I'd like to invite maybe 2 questions for the next discussion in 10 minutes. Okay, please raise your hand or just write in the chat box. Okay, maybe I start one question, Professor Mubarak. This is the high pressure acid leaching involves the very high pressure, about until 55 atmosphere. So how to achieve with such a high pressure? Maybe you can elaborate.
Yes, so basically we use isolated reactor, Teflon reactors to resist from sulfuric acid, and we isolate it and heat it. So the steam generated from the heating of the solution is retained there and give the pressures. And we measure the pressures around 40 to 45 bar. So basically using the vapor generated from the heating of the solutions, yeah. And we have calculated the solid liquid ratio in order to have a certain vapor pressure, yeah, we required for this leaching.
Okay, thank you very much. Okay, there is one question from Dr. Nurdi Subagja from PR Metallurgy. You mentioned that magnesium creates scaling problem in HPAL process. I'd like to know how to handle magnesium scaling problem in the process. Okay, please, Professor Mubarak.
Thank you. So in industrial scale, it is done by adjusting the feed composition. So make blending, etc., to limit the magnesium content and also aluminum content. And then periodically, if scale still happen, the plant must be stopped, and scale is removed by rinsing the reactors by hydrochloric acid. This is what is done in industrial scale. In laboratory, yeah, in our case, it's not a problem. But if it happened, yeah, we remove the scale manually by removing from the wall. Yeah, actually, this is what what I can answer to your question.
Okay, thank you so much. Pak Rudi, always it is.
Okay, thank you very much, Professor Jaki, for the answer. Thank you.
Thank
Okay,
you,
thank
Pak
you so
Rudi.
much. And again, another question from Pak Iwan Setiawan. HPAL, so it's in Indonesia. Sorry, Indonesia. HPAL merupakan proses yang paling banyak dipilih saat ini. Saya menemukan bahwa HPAL seperti Murin Case and Bulong Project berakhir. Apa penyebabnya dan bagaimana mengantisipasinya? And one question, HPAL is okay. It's the same one in English.
Yeah.
Okay, please.
Yeah, Pak. So basically, at the moment, the HPAL technology has been on the 4th generation. So the first one in Moabay in Cuba, 1955 already, very long time. And the second generation you mentioned here in Western Australia, Murin, Kosi, Bulong, they face problems, and the problem is basically mechanical and operational problem related with what I have mentioned before, scaling, corrosions, and what is the consequence? The consequence that the plant cannot attain or reach the design capacity. And then come the 3rd generations, such as Ramu, Ravenstop, and then Coralbay, Takanito. They learn from the problem faced by the 2nd generation of the HPAL. So they adjust the equipment, the titanium cladding, the valve, and also the most important is also adjusting and the feed compositions. And the most recent progress is this chromite removal. Chromite is the constituent in the ore that give abrasions to the reactors, to pipeline, to the valve, and the recent technology developed with chromite removal by gravity concentration before the ore is treated in HPAL. And at the moment in Indonesia, this is basically already the 4th generations, and developed also by the engineering company. It has been developed the same, HPAL plant in Papua New Guinea. So if your question is how to anticipate for HPAL plant in Indonesia, it seems that they can learn from the previous experience. And just this year's they report that the production capacity already reached 110% of design capacity. So it seems the design capacity is not the problem, but they're facing the problem of how to deal a huge volume of tailings. This is what they face right now, but still, but I think they can manage this. Okay.
Okay, thank you so much, Professor Mubarak. How about Iwan? Is this answered your question? Okay, thank you so much. Okay, I'm sorry, Professor Mubarak. Maybe there are still many questions or people want to contact you. So maybe you can also write your email if
okay,
so.
Yes.
That's it.
Okay,
Now I think
I write in the chat room. Okay.
Yes, thank you very much. So I thank again Professor Zaki Mubarak for the second plenary talks. I think it's very interesting topic, and we hope we can collaborate each other with scientists in Indonesia and our scientists in abroad. Thank you very much. Let's applause Professor Mubarak. Thank you so much. Okay. Now let's move to the third speaker in the plenary talks here. That is Professor Lydia Wong from NTU. Good day, Professor Lydia. I hope you are doing well.
Yeah, good morning, Pak Albertus. Can you hear me? Hello. Can you hear me? Sorry. Hello.
Okay. Hello, Professor.
Can you hear me? Is it okay?
Yes, yes.
Okay,
Yes,
good,
that's
good.
great. Yeah, thank you for coming. Now it's the time for your presentation. At first, I'd like to introduce Professor Lydia. Dr. Lydia Wong is an associate professor at the School of Material Science and Engineering and MSE from Nanyang Technological University, NTU, Singapore. She presently serves as assistant chair at the School of MSE Cluster Director at Energy Research Institute and NTU, and secretary of the Material Research Society of Singapore. She graduated with Bachelor of Applied Science, First Class Honors, and Doctor of Philosophy, both in Material Science and Engineering from NTU. After her PhD, she worked as a senior engineer at Chartered Semiconductor on advanced microelectronic devices. She was also a visiting scholar at the Department of Chemical Engineering, Stanford University. And Professor Wong joined NTU as a teaching fellow in 2008. Professor Wong's research interest is in the structure of chemical modification of semiconductor materials for clean energy and electronic application. She has published more than 150 publications in international peer-reviewed journal and cited more than 9,500 times. She has given invited talks as well as organized symposia at international conferences such as MRS Spring, and EMRS, ECS Spring, etc. She was also an editor of journal Material Science, Material in Electronics from 2018 to 2019. He was a guest editor for Journal of Material Chemistry. She presently sits as a editorial advisory board of Solar RRL Bile and serves as a member of Citizen Consultancy Committee at Nanyang Constituency. As an advocate of innovative teaching methods, Professor Lydia has received a number of teaching awards such as Nanyang Education Award, Honor Teacher of Ko Hoon Hui Award, and MSc Teacher of the Year Award. Professor Lydia Wong is also active in promoting science and engineering to Indonesia youths through her outreach talk and collaboration with Indonesian universities. She has been serving as the managing director of Ikatan Ilmuwan Internasional in Indonesia International I4 ASEAN since 2020. Oh, it's incredible biography. And today, Professor Lydia Wong will deliver a talk entitled Advanced Materials for Next Generation Solar Harvesting Devices. Okay, Professor Lydia, time and screen are yours, please.
Thank you very much, Pak Denny, for the very complete introduction. There's no need to read everything. I leave you to actually pick up a few things, but thank you very much. But something that Pak Denny did not mention just now, I was actually born and raised in Indonesia. So I actually finished my SMA in Jakarta before I went to Singapore to do my undergraduate. So selamat pagi, Bapak Ibu semuanya. I'm very happy to be invited, and I also thank the organizer for inviting me. I think it's really an honor to be able to share our research activities with all of you here from BRIN. So if you may allow me to share my screen. Okay, are you able to see my screen now?
Yes.
Okay, do you see my big screen, or is the
still not big screen? I think still.
Oh, still this. Okay.
Yes.
Okay. Let me stop share and see if I can change. Okay. How about now?
Yes. Okay. The screen.
Okay. Good. All right. So the title of my talk today is Advanced Materials for Next Generation Solar Harvesting Devices. So given the probably wide expertise and interest from everyone in this symposium, I would try to keep my presentation as broad as possible. So imagine this like a buffet session, yeah, so that you get to know the activities of my group. I will not go into too much details, but all of the materials that I talked about today has been published. So you are most welcome to take a look at our group publication. Okay, I would like to start this talk by sharing this. Our world is in crisis. I think many of us have agreed that our livelihood in the last 2 years have changed because of COVID-19, right? There is a rising death rate. Families are separated because the borders closed. I myself have not been back to Indonesia for 2 years because of COVID-19. Only last month I managed to go back. But then, fortunately, science come to the rescue because of now we have faster and more convenient detection and cheaper detection as well. So now we can do a rapid screening. New vaccine is available, and now I think most of us have been vaccinated. And new medicine also will be available soon, or already available. So also there's also a new face mask, right? So soon COVID-19 will be part of history, yeah? Now, other than COVID-19, we also heard a lot of stories about the increasing, I think now also the BBM price has been increasing, right? And this is not only because of the crisis in Ukraine, but also in general energy crisis in the world. And I'm sure everyone here agree that the threat of global warming is real, yeah, it's not a hoax, yeah. And if the Earth temperature increased by 5 degrees C by 2100, Jakarta, Singapore, and Beijing will disappear because of the rising sea level. So now the question is, can we use science to make our planet green again? Yeah, this is something that we all have to think together as a community. So in NTU, okay, NTU has already started to do a lot of green initiative, including implementing what we call as NTU Eco Campus. So in our campus, we have 5 megawatt solar panel installation. This is an aerial view of NTU from top, and you can see almost all of our rooftops have been installed with solar panels. And this is the largest installation of solar panel in a single location in Singapore, because you can imagine Singapore is a very small country. Probably the size is only 700 kilometers square. Yeah, so you can imagine it's probably only 20% of Jakarta or even less. And NTU itself provided the highest installation of a solar panel in a single location. And assuming that the solar cell has 20% efficiency, actually, if we can cover the whole Sumatra with solar panel, we can fulfill the world's annual electricity needs. So that is how powerful solar cell is. So if we take a look at the slight history and evolution of solar cell, we can see that solar cell has evolved to 3 generations. The first generation is silicon solar cell. This is, I think a lot of us are familiar with this, and it has been installed in many rooftop solar farm as well as floating solar farm. However, the limitation of silicon is it is a rigid substrate, okay, and it is heavy. So 2 meters square of solar panel actually weigh around 25 kilograms. So it's around the weight of your luggage if you go overseas. Yeah, so it's not easy to transport this. So you can imagine Indonesia having 13,000 islands. The cost of transportation of solar panel to the remote island is actually much more expensive than the solar panel itself. So now, can we change the bulk and heavy silicon to a lighter solar panel? In fact, a thin film solar panel that can be printed on flexible substrate, on plastic or stainless steel, so that they can provide the same amount of power on a much lighter material. Yeah, so power per density is actually much lower for the second generation solar cell. So the material used for the second generation solar cell are amorphous silicon, cadmium telluride, CIGS, DZS, etc. The third generation of solar cell are usually defined for the more exotic materials such as organic materials, dye-sensitized solar cell, or perovskite solar cell. So this is much thinner than the second generation solar cell. However, most of the third generation solar cells are not very stable. So the lifetime of third generation solar cell is usually less than 5 years, while the gold standard in the industry is the silicon, which has a warranty of at least 20 years in installation. At least now I heard they can go up to 30 years. So now the challenge for the third generation solar cell community is, can we produce high efficiency solar cell with a stability as good as silicon for 20 to 30 years? Yeah. So my group has been working on all type of solar cell, yeah, second generation and third generation of solar cell, except for silicon, because what we are trying to achieve or to understand is, can we make solar cell beyond silicon that will serve different types of application. For example, a transparent solar cell that can be installed on a windows. And this is an example of installation of a solar panel in a bus stop in Melbourne. So this is done by one of our company collaborator, Clearview. Yeah, or maybe we can actually install a solar rooftop on electric vehicle, yeah, or use different type of solar cell that will allow only specific wavelength to go through a greenhouse, so that the plants can still grow, but at the same time the solar panel will be able to provide electricity that powers the greenhouse. Yeah, so these are all innovations in materials that enable solar cells beyond silicon, and we strongly believe that new application needs new materials. So the outline of my talk today will be as follows. I may not be able to go through everything, but some of the items are emerging inorganic photoabsorber. So I will talk about casterite and low dimensional antimony sulfoselenide. And I'll share a little bit more of our activities in semi-transparent perovskite solar cell, as well as iron oxide-based photoanode for solar water splitting. So a brief introduction of CZTS, or copper zinc tin sulfoselenide. Yeah, this material has a suitable band gap for solar absorption, high absorption coefficient, and ability to be produced as a thin film. Okay, and if in Indonesia, as we have a lot of natural resources, you would realize that all the elements in this material are available in Indonesia. Yeah, copper, zinc, tin, sulfur, and selenite. However, the problem with casterite is, even though based on the band gap, the efficiency can reach 30%, but the demonstrated efficiency in the lab is around 14%. And what is the problem of this is because, okay, I try to cut the story short, but the main reason is copper, zinc, and tin, the three elements in this crystal structure, has very similar atomic size. So what happened is, these three elements, the red, the white, and the blue, they tend to interchange within the crystal lattice and create what we call as anti-side defects. And these anti-side defects manifest themselves as electronic defects between the band gaps. So they can exist as an acceptable level, impurity, or tail states. And all of these are very detrimental for electronic properties. So the question is, can we have a defect-tolerant casterite? Now, casterite is the crystal structure that we use to define this technology. Yeah. So knowing that the main problem is the similar atomic size of copper, zinc, and tin, we look at the periodic table. and we see what are the elements that we can use to replace copper, zinc, and tin without changing the crystal structure of casterite. So in this periodic table, there are a few elements that have been, actually there's a lot of elements that have been investigated in the world. Yeah, the one highlighted in orange is actually already reported as an alloying element. The one that is highlighted in blue has been included in CZTS as dopants, and the one in yellow is some other elements that have been reported but not very often, while our own group has investigated those that is circled in these black boxes. All right. And if you're interested to find out more, you can take a look at our invited review article in Journal of Physics Energy. And these are all the publications that our group have done. However, the question is, what is the general rule of selection? What can we, how do we choose based on all the material in the periodic table? Yeah, so in our recent paper, only published this year in Journal of Materials Chemistry A, we do a systematic investigation of substituting zinc with different elements. Yeah, because many of the reports in literature, they actually make the material with different synthesis method and measure using different characterization techniques. So we were not able to have a good understanding on the main reason for the properties. Yeah, the structure properties relationship is not very well established. So in this paper, we look again at the periodic table and we list those that has a cation with a +2 oxidation state. And then we list their electronic configuration, we check their earth abundancy, their toxicity, as well as their ability to produce a quaternary chalcogenide, or as their ability to form a tetragonal structure. So after we look at this, we narrow down our selection to these materials, and all these cations have a +2 oxidation state and have different cation radius with zinc and copper in a 4-fold coordination. So we synthesize them, okay? Our synthesis method is very easy to replicate. Our group use a lot of solution process. So I talked to many friends in Indonesia. This is something that you can replicate in Indonesia because what you need is some metal salt diluted in a thiourea solution. And then you need to use a spray head and spray this solution on a heater. Yeah, we heat this at around 450 degrees C. And then the film will be formed. The solvent will be evaporated during the spray pyrolysis. And then we will form the film. And after that, we heat up this substrate in a furnace. So within this furnace, we have a sulfur source. And then this is a process called sulfurization or selenization. So the crystallization process is happening here. So after we have this film, and then the next step is to do chemical buff deposition. And finally, this is our solar cell device. Yeah. So this is the cross-section SEM of the different types of casterite with different substitute of zinc. So when we have manganese, this is the crystal structure. When we have magnesium, nickel, iron, cobalt, barium, and strontium. Yeah, so we can see that certain element produce a bigger crystal structure than the other elements. So we also look at the XRD of these different types of material, and we can further classify them. The bottom here, when we substitute zinc with manganese, iron, and cobalt, we manage to have a tetragonal structure. Yeah, either is a stannite or casterite. However, when we use nickel or magnesium, they don't actually form a single crystal structure. In fact, they separated and form a nickel plus copper tin sulfide. When we use strontium and barium, the crystal structure changed from tetragonal to trigonal. Yeah, so this is our structural investigation. And we correlate this with the Hole concentration and hole mobility, which is measured using AC Hole measurement. And we see that certain types of dopants produce a very high hole concentration, meaning they are more metallic than semiconducting, for example, for manganese and iron, as well as cobalt. Yeah? And then after we do the optical and electronic characterization for the thin film, we also make the solar cell. And from the solar cell, we can see that actually not all dopants can produce a good solar cell photovoltaic properties. Yeah. So the good ones are actually observed for manganese, barium, and strontium. Yeah, all these three elements. Okay, and we also measure EQE based on this. Okay. All right. So based on our investigation, actually, I just want to cut the story short. The most promising is when we substitute zinc with cadmium. Unfortunately, this is also a toxic material, but cadmium has a lot of good properties. Okay, cadmium radius is much higher than copper and is theoretically predicted to reduce the formation of the deep defects. And the crystal structure of CCTS, or copper cadmium tin sulfide, is stannite, which is much more ordered compared to the casterite structure. So we synthesize this material and we verify the crystal structure, and we also collaborate with a theoretician group from Professor Emily Carter's group, and we discover that the cadmium substituted CZTS has a higher formation energy for the defects. So in other words, CCTS is less defective than CZTS. We also measure the EQE of this material and we compare with the CZTS. It has a much sharper absorption edge, which indicate a much reduced band gap fluctuations, an increased PL intensity, which indicate reduced non-radiative recombination, and increased PL decay time. Yeah, so we make a solar cell, which is now is 8% efficiency. This is one of the highest for new casterite materials. Okay, now I changed the topic a little bit of another material, which is also interesting. This is antimony sulfide, much more simpler crystal structure and than the CZTS. Now, this material also has a very, very interesting band gap and absorption coefficient, very suitable for solar cell. The challenge in antimony sulfide is it tends to form ribbons, okay? And the conductivity is not the same. So the conductivity in the HK1 direction is much higher than the HK0 orientation. So ideally, if you want to have a good solar cell, you need to have sp2s3, which is well oriented in HK1 orientation. However, if we see the literature, most of the record efficiency antimony selenide in literature still have a HK0 orientation. Very few look at the HK1 orientation. So what our group did is actually trying to engineer the growth of antimony sulfide by using a seed layer. In our seed layer, we use a combination of tin oxide and cadmium sulfide because we know that when cadmium sulfide is oriented in this direction, 100 and 101, it will actually provide a very nice template for antimony sulfide to grow in HK1 orientation. So this is what we did, and what we discover is actually very interesting, right? We add a little bit of cadmium during the hydrothermal synthesis of antimony sulfide. And what we found is when we don't have cadmium, okay, this is from the XRD, the red color represent the HK0 orientation, HK0 orientation of sp2s3. The green one represent the HK1 orientation, which is the good orientation. So if you don't add cadmium, you have a large proportion of the red HK0 orientation. But as you increase the cadmium in the hydrothermal reaction, the proportion of the green HK1 orientation increases and much more dominant than the red one. So what happened? So this is our proposed mechanism, which we will verify using TEM later. Yeah. So this is our crystal structure. This is our cadmium sulfide as the seed layer. Cadmium sulfide has 100 or 101 orientation. Okay, we actually wanted cadmium sulfide to all grow in 100 orientation. To have a good seed for the SB2S3 to grow vertically in 101 orientation. So the top layer here is the SB2S3. So what happened when we add a little bit of cadmium during the growth of SB2S3? This cadmium actually repair the bond in 101 such that it flatten out the cadmium sulfide and make all the cadmium sulfide oriented in 100 orientation and provide a good template for the growth of antimony sulfide. So this is the illustration. At the beginning, okay, CDS, cadmium sulfide, has this profile. So on the green 100 orientation, we can grow a vertical SB2S3, but on this part, we have a horizontal 100 SB2S3, which is bad. As we have more cadmium, we flatten out this seed layer, and at an optimal concentration, we have a nice epitaxial growth of 001 SB2S3. But if you have too much cadmium, what will happen is this facet, the 101 facet, will grow again. And as a result, you will again have a mixture of horizontal and vertical SB2S3. Yeah. So we verify this growth method with high resolution TEM. I don't want to go into detail, but anyway, we verify this. We make a nice efficiency, 9%, which is one of the highest for SB2S-SE3. And we report this in advanced materials. So this is more optical characterization to verify the reason behind the improvement in efficiency. So this is one method. And just to add on, all of our fabrication method is using solution process. So this is something you can do easily in your lab just by using a hydrothermal reactor and a furnace. Okay. Okay. Okay, maybe I don't have much time, but I just want to share that our group is also working on perovskite. Yeah. So we actually use copper sulfide or aluminum doped copper sulfide as a whole transporting layer below perovskite. And the main function of this copper sulfide is actually to anchor the lead. Yeah, so this sulfide actually can react with lead and stabilize the lead structure in the perovskite itself. Yeah, so we in this study we changed the whole transporting layer with different types of material: nickel oxide, copper sulfide, aluminum copper sulfide. The efficiency is comparable, around 12%. And I think to cut the story short, what happened after 48 hours is that now, okay, maybe I jump too fast. Perovskite is very well known to be very fantastic materials with high efficiency, but very bad stability. So I actually recommend to all my friends in Indonesia, if you don't have a glove box, don't even need to make perovskite because it will die immediately after you spin coat. That's what happened to us in Singapore as well, because Singapore and Indonesia has very high humidity, 80%, 85%, right? So if you don't have a glove box, don't even bother to make perovskite. You're going to waste your time. So this is what happened. If you, even this is 75% humidity at 20 degrees here, you leave this solar cell after 48 hours. If you have a nickel oxide as the whole transporting layer, your film will degrade. When you use copper sulfide and aluminum copper sulfide, the film remains stable, and you can see the efficiency remains stable over a prolonged period of time as well. Yeah, and we further investigate the reason behind this is because if you use nickel oxide, after seven days, you can observe the formation of this delta FAPBI3, which is detrimental, which is bad. But if you use copper sulfide or aluminum copper sulfide, you don't see this peak. So this is really, the sulfide really binds lead and prevent the formation of the detrimental FAPBI3. Okay. Okay. So so for those who are interested to learn about emerging chalcogenide thin films for solar energy harvesting, I strongly recommend you take a look at this review paper that we published in Chemical Reviews. Treat this as your textbook, because everything you need to know here before you start research in this area has been summarized in this review paper. Yeah, it's 80-page long. Don't read on one day, read a little bit by a little bit, but this will definitely set you on the right direction. Okay. Now, in terms of perovskite solar cell, I don't have much time. I think I will skip a few. So I just show you that our group also work on a semi-transparent perovskite solar cell for window application. And we are actually, okay, if you look at this table here, this is efficiency as a function of solar cell area for solar cell with transparency higher than 20%. So most of the reported paper are reporting solar cell area of 0.1 cm square. So this is very small, and the efficiency is around maybe 9 to 10%. What we report in this paper is we are able to achieve 12% efficiency for small area, and for large area, which is very, very not many people reported. We actually reported up to 10 to 12% efficiency. So this is also a very interesting area of research, how to make semi-transparent solar cell for Windows application. Okay, now I change a little bit. I have 5 minutes to cover this second part. So we talk about global emission, and I think most of you know that a lot of global CO2 emission actually come from transport. So the question is, can we change our fuel from BBM to hydrogen, right? Hydrogen. So one way to generate a clean hydrogen is by artificial photosynthesis. In photosynthesis, we know that the plants actually do this very efficiently. They actually change carbon dioxide and H2O with the help of the sun into carbohydrate and oxygen and water. So we try to imitate this process in order to generate hydrogen, which can be used as a hydrogen fuel cell to fuel our transportation in the future. There are many methods to do this. The first method is particle photocatalysis. So this is dispersing of nanoparticles, semiconductor nanoparticles that can absorb light and generate hydrogen and oxygen spontaneously in water. This is a simple design, potentially low cost in long term, but this is challenging to scale up, has a low stability and low solar to hydrogen conversion efficiency. The second approach is using a photoelectrochemical cell where you have a photoanode and photocathode. You shine light on both of them. The semiconductor is coated as a photoanode or photocathode. Oxygen is generated in photoanode. Hydrogen is generated in photocathode. Okay. This is more complex design, but will save more space. Yeah. But the efficiency is still not very high. The last approach that is the most easily converted into commercial application is the photovoltaic electrolysis tandem or photovoltaic PEC tandem. So in this configuration, we use a photovoltaic or solar cell to absorb light, generate the voltage required to drive the reaction of oxygen evolution reaction in the anode and hydrogen evolution reaction in the cathode. Yeah, this is the easiest to be implemented in real life. However, it will require, it's more expensive because you need catalyst as well as solar cell, and you need a bigger plot of land. Yeah, so these are the different types of solar to hydrogen generation, green solar to hydrogen generation, but there are a lot of efforts in the world to realize this technology. For example, European, Australian, as well as US, they have a lot of initiative in this area. Yeah. So our group have done many of this. In photoanode, we have done iron oxide based photoanode. I think just some of these are also abundant materials available in Indonesia. And I think, okay, and as an example for what we have done in solar cell, we have also done CZTS as a photocathode for solar water splitting because of the interesting properties. And we have shown this together with Professor Kazunari Domen in University of Tokyo. We published this in 2018. We use CCCTS, and the interesting part that I want to share here is that this is really a collaboration because our group know how to make good CCTS material. I send my student to spend about 1 month in Professor Domen's group in Tokyo. I pay for everything, and he go there to learn how to code this CCTS nicely. After he come back, he write this paper and we co-publish together. So I think I strongly encourage a lot of collaboration between research group in order to realize a good, meaningful, high quality work. Yeah. This is another work that we are doing, CZTS also. I wouldn't go into details here. In terms of hematite or photoanode, we have done a lot of things. So basically for hematite, the challenge is for iron oxide, we have to make it nanostructured. If it is not nanostructured, people have tried for 20 years, nothing happened. Only when they do nanostructuring, then an efficient photocatalysis can happen. Yeah. So we can do this either by nanostructuring plus dopant and surface treatment. And we have done this through many initiatives over the years, more than 10 years ago, and published in different publications. So if you're interested in this area, again, my method is solution process, easily fabricated in a chemical lab anywhere. So you can take a look at some of our publications. One example here is combining perovskite solar cell with hematite photoanode. So we combine them in a series. This is the perovskite solar cell. This is the photoanode. We shine light onto them, and we are able to generate unassisted water splitting using perovskite solar cell, and we have a pretty decent solar to hydrogen efficiency. Yeah. Another materials that I'm working on is bismuth vanadate. Yeah, I think many of you probably also have heard about this. This is also one of the good material for photoanode. Even though the main limitation of this material is the band gap is too large. The band gap is 2.4 eV. So even if we reach the limit, theoretical limit, right? Theoretical limit of this BVO is only around 10% solar to hydrogen conversion efficiency. And this is not going to be attractive in terms of cost. So the only way to improve the solar to hydrogen efficiency is to reduce the band gap of bismuth vanadate. And how to reduce the band gap of this material? We have to search for a new type of vanadate. So different types of vanadates like manganese, copper, or iron have lower band gap than bismuth vanadate. So our group tried to make iron vanadate. This is also done very interestingly using accelerated discovery or high throughput synthesis. So what happened is my student, Hip, she actually make many different composition of iron vanadate using different dopants on the same piece of paper, on the same piece of substrate using inkjet printing. Yeah. And then we analyze the photoelectrochemical properties using this scanning droplet cell. And then we discover which percentage of dopant reach the highest photocurrent. And then we discover that chromium is actually the best. And we make a proper photoelectrochemical cell based on that. So this is also a very interesting discovery that can also be related to the machine learning. Yeah. Okay, so this is the summary of my talk, design and discovery of next generation of photo absorber with superior quality still needed. Yeah, you need a lot of good properties, and we need to have interdisciplinary research, including theoretical prediction, machine learning, high throughput experiment, and characterization in order to be able to produce the next good material. For example, everybody knows about perovskite nowadays. Can we produce the next perovskite? Yeah. Okay. So this is an overview of my group activities. I deal with all of this. You can take photo of this, yeah. And I would like to acknowledge my team member. I think none of this would have happened before, if not because of them. I have a very international group member. 2 or 3 of them are from Indonesia. I have Indians, Vietnam, Egypt, China, Singapore, Malaysia, yeah, India as well. So if you're interested, feel free to contact me. There's always opportunity for postdoctoral fellows as well as research student scholarship. If your result is good, we will welcome you. Yeah, and I also have a lot of collaborators all around the world. I think none of this will be possible without them. And let me just advertise. Okay, you can take photo of this. We are organizing an international symposium in Singapore next year, 26th to 30th of June 2023 in Singapore. And if you're working on inorganic materials for solar energy harvesting, please submit abstract to Symposium O. This is the symposium that I'm organizing. Abstract submission closed on the 2nd of January. These are all the invited speakers. If you're familiar, they are all very renowned scientists. And the good news is papers presented in this symposium will be considered for publication in Journal of Materials Chemistry A, and the impact factor is around 15. So if you are interested, please feel free to submit to this symposium. So with that, I would like to conclude my talk. And with this message, the future of our planet is in your hands. So thank you for your attention. Thank you very much.
Okay, thank you very much, Professor Lydia. It's very interesting, comprehensive, and broad talks about solar harvesting materials. It's very great, and I'm also glad that Professor Wong groups are open for us to collaborate, including also into the invitation for the next conference in Singapore. Okay, Bapak Ibu participants. Now I would like to invite question and comments. Please just raise hand or write in the chat box. Maybe we still have 1 or 2 questions for 5 minutes discussion. Okay, maybe I will start one question with Professor Lydia. So the problem maybe for the solar harvesting materials here is to scale up the production maybe of the material itself. What is your suggestion about this, and especially for the next generation, for the last generation of chalcogenic and perovskite orchestrite in the materials? Maybe very
nice, very good question, Pak Denny. Yeah, I think this is also the next stage of research. Many groups now look at scaling up of production. So we have shown that small scale solar cell has very high efficiency. Now the question is, can we make it large scale? And I think we need to work closely with industry, with the designer of the machine, designer of the equipment, right? Because we know the process, we know the chemistry, but to design an equipment is not an easy task. So we really need interdisciplinary collaboration with people from mechanical engineering, from electrical engineering, etc. But I think there are groups who have shown this. Many people in China and for example, in China and in UK, there are a lot of startup companies to scale up perovskite solar cell. And there's 1 or 2 companies in Europe as well that is looking at scaling up of CZTS solar cell using a roll-to-roll process. Yeah.
Okay, thank you so much. Okay, Bapak Ibu, maybe there are 1 or 2 questions. We still have another 3 minutes. Okay, please just raise hand or write in the chat box.
Denny, can I have a question for Denny?
Oh yes, of course, Professor.
Not a professor.
Please. Yeah, thank you, Bu Lydia. It's very nice and very comprehensive presentation.
Thank you.
Very amazing. Okay, Bu Lydia, I have a question. You said that in the presentation that you seek a kind of fundamental principles in how can I say? Usually in photocatalytic we engineer. Sorry. So usually we engineer how to decrease the band gap. So our group have used many things by doping or by making a kind of oxide, something like that, but we don't know the mechanism yet. So we just measure the band gap, but still we don't know. So just you said in the presentation that you will try to select to choose from the periodic table the elements that suitable to for the process. Actually, I guess it is to. Can I? My voice is heard or not?
Yeah.
Okay. So can you explain briefly? Maybe I missed your part of the presentation briefly about the fundamental principle to reduce the band gap. Okay, and the second question is in the presentation, the last part of the presentation, you said about how to reduce the carbon dioxide. So it's how to mimic the photocatalysis process from the plant. So if I'm not mistaken, I haven't seen the sample of the experiment about how to reduce the carbon dioxide. Okay, that's two questions. Thank you.
Okay, let me just get the slides. Okay, hold on. So first is on the selection of the materials, right? I want to clarify that for the periodic table that we show, right? Okay, let me share the right screen with you. Can you see the slides?
Okay.
Yeah.
See that.
So for this one, our goal is not to reduce the band gap. Our goal here is to reduce the defects. Yeah.
Oh, okay.
So for this one, we want to replace copper, zinc, and tin with other elements that is bigger, so that they do not form the anthracite defects. So we choose our criteria of selection is they should have a 2+ oxidation state. Okay, and then after that, the rest is they are earth abundant and non-toxic. And then thermodynamically, they should be able to sit in a tetragonal structure. So that is our basis of selection. So the target is to reduce the defects. Yeah. So this is the first option. For the other one on CO2 reduction, okay. So I did not go too much details, but what we have done a lot actually in this area, let me just show you. Yeah. So this is one example. One example is using the CCTS as a photocathode. So this is generating hydrogen. This is our solar to hydrogen conversion efficiency. Yeah, so this is a IV measurement. So this is a photocatalytic reaction. We provide potential to this configuration, and we measure the photocurrent detected at 0 voltage versus RHE. So this is actually the electron generated from this reaction. And we measure the gas using gas chromatography. We verify that the gas generation is hydrogen. So this is the demonstration of actually half cell reaction. Yeah, half cell reaction of this photoelectrochemical cell. We have also done many things in, okay, so this is another example. We use hematite or Fe2O3 as the photoanode. This is powered by perovskite solar cell. So the perovskite solar cell provide the voltage to drive the reaction. And this is the data that we have. This is the current density of the photoanode. This is the current density of the perovskite solar cell. And this is the current density of the tandem cell. So we have demonstrated some of this, probably not the best in the market or in the world, but our lab has the capability to build the device and measure it. Yeah. I hope I answer your question, Pak Solihin.
How about the carbon dioxide releasing? Okay.
Okay, that one I did not include in this presentation. So what I am trying to say is, if we can make hydrogen, right, we can actually reduce the usage of fuel of BBM, right? So we can make H2O. But actually, I have another student who is working on CO2 reduction. We are still in the process of publishing the papers, so I have not included them in this presentation. But I hope I would be able to share more with you next year.
But this used by using photocatalytic materials? Okay.
Yes.
Okay, thank you very much, Bu Lydia.
Yeah, thank you, Pak Solihin, for the question. Okay.
Okay, thank you very much, Pak Solihin and Professor Lydia. Now, I think Professor Lydia has a limited time. I think it's time for the.
If you have, I think actually I can. If there's one more question, I can take one last question before I.
Okay.
Are there more questions?
So, maybe one more question for Professor Lydia because time. Professor Lydia is so precious.
I just happen to be very busy these few days.
Okay.
Yeah. I think we are all busy.
Yeah. Okay, one more question. I invite.
If not, then it's okay. Yeah, it's okay. You can always email me. Yeah, I have. You can just Google me and then you can find my email address.
Okay, then. Thank you very much, Professor Lydia Wong from NTU Singapore. I'm glad and very pleased and appreciate of your talk and attendance to our ISMM conference here. So once again, let's applause Professor Lydia Wong for
thank you very much. Thank you.
And yes, and I'd like to thank again all plenary speaker here. Dr. Rizwan Rashid, Professor Saki Mubarak, and then Professor Lydia Wong. And now I think I will close the plenary session and we will move to the next parallel session. But before that, I will return the time and screen to MC, Mbak Talita. Please. Thank you very much.
Thank you, Bapak Dr. Albertus Denny, for guiding our plenary session this morning. Thank you for all keynote speakers for the presentations, insight, and knowledge. They are also very inspiring. So after this, we will have a break for about 45 minutes to 1 hour. I think at around 1:15 p.m., all participants or all presenters should be ready on the parallel session room. So everyone, please bear in mind, you might have attention with your paper number and make sure that you enter the room based on the schedule. So for all the moderators and the managers or and also the set manager, I mean, you are also invited to enter your room parallel sessions. So I will close this second morning session of ISMM 2022. My name is Talita Asmaria. Thank you for your all attentions. More and less, I do apologize. Wassalamualaikum warahmatullahi wabarakatuh, and see you in the next opportunity.
Waalaikumsalam warahmatullahi wabarakatuh.
Waalaikumsalam.
Waalaikumsalam.
Jadi kan dari satu hari akan tidak juga tetapi sampai rumah ada jadi dia ini dulu.
Ya, berarti sih itu aja. Hari ini.
Sekarang dulu.